What is up, you guys? So in this one, we'll be talking about decision trees to perform classification and regression tasks. We're going to, start with the theoretical background of decision trees. We'll be defining some metrics such as Gini Impurity, the entropy, and talk about the CART algorithm as well as how it operates, why it's suboptimal. Then we'll be seeing some Python implementations and sensitivity analysis on decision trees, both for classification and regression tasks. Last but not least, by the end of this lecture, we will be showing how to use decision trees for stock market analysis. I hope you're excited as I am. Also consider subscribing to the channel, liking the video, and leaving a comment down in the comment section below just to show me feedback. YouTube algorithm recommends my videos to a larger audience if you subscribe to the channel, like the video, comment, and show support to the channel. So I hope you're excited as I am. So without further ado, let's get started. Now, the most reasonable way to view decision trees are that there's sort of a question answering model. So you've got your training data X, your target values Y, okay? X is a matrix, let's say M by P, so M instances or examples and P features. Likewise, Y is a vector of size M by 1. In the classification case, Y takes on discrete values, whereas in the regression or continuous case, it takes on continuous values. Now, decision trees are applied both for classification and regression tasks. So let's say as an example, I've got my X that contains the following data. Well, 1, 2, then 3, 5, and 7, 9, and then maybe 11, 12. And my Y, we're doing a classification problem over here. So my Y contains either 0 or 1, for example. We're doing a two-level classification, so 0, 0, 1, 1. So decision trees, what they do is that they build a tree based on some cost. And this tree is actually built up recursively and through some sophisticated intuitive algorithm called the CART algorithm. CART stands for Classification and Regression Tree. It's a greedy algorithm that splits up your data to minimize some cost. So the cost here really depends if you're working in a classification, if you're doing classification or you're doing regression. So let's say for the moment we're doing classification. Your cost J, let's call it J, will then depend on two things. It's the feature index K and a certain threshold, let's call it, I don't know, A, that depends on K. So if I were to draw my data that I had over here, right here, if I were to draw them in a 2D plot, I can draw them as such. So let's say this is my X1, feature 1, and X2, feature 2. So let's say my class 0, which is 1, 2, first example. So 1, 2, let's say it's over here. And 3, 5, let's say it's over here, somewhere over here. And the other two, say they're over here. This guy is my 1, 2. This guy is my 3, 5. This is my 7, 9. And here's my 11, 12. Okay? So this CART algorithm starts with the first feature, let's say X1, and tries to fit a certain boundary denoted by a.k.a, the threshold. Where should I, segregate my data to minimize my cost, J? And we'll be revealing what J is. Since we're in a classification approach, then the mean square error doesn't really fit. So what we're going to do is try to separate the data based on another cost. So let's say I found that this position, according to the cost that we're going to say, is the best position. So here's where A1 is going to be. So this is my value A1, right? For feature X1, of course. Now, how did I pick my A1? Well, the algorithm starts with J1, A1 by separating my data into two classes. Let's say class 0 and class 1. So it will be M0 over M times J0 plus M1 over M times J1. Okay, let me remove the numbers off the graph because they're really distracting. Okay, so now what is J0 and J1? Well, since we're in a classification problem, then normally what people use are two types of costs. The first one, which is known in the machine learning world, is the Gini impurity. Okay, and what the Gini impurity is, it's computed as follows. So it is 1 minus the sum k running from 1 till p, where p is the number of features, the probability over the kth instance square. Okay, actually pk is not a probability. Well, you could view it as a probability, but it's more of a ratio. It's a ratio of the number of k instances among all the examples. So what does that mean? In our small example, and assuming that we start at the root, that is, we take all our data, that is m is 4, we've got obviously two nodes at the left of A1. So M0 is equal to 2. Likewise, we've got M1 is equal to 2 in this simple example. Okay, so if we were to compute the impurity in that case, then for this particular question, is my x1, let's say I stands for ith instance, is it less than A1? If so, classify it in 0, else classify it in 1. Then if I ask the question, is my x1i less than A1? If so, if that's the case, if this is true, then what is my classification now? I ask myself the question, where am I? Where do I stand in this simple classification problem? Am I done? Well, if it's less than A1, then what do I have in my hand? All I have is that two guys are classified as class 0, whereas no one is classified as class 1. So now you ask yourself this question: what is the impurity of this arrangement? Well, over here, my J0 is, using the definition, 1 minus k going from 1 till p, where p is 2, pk square, right? Let's zoom in over here. That is 1 minus p0 square minus p1 square. Well, I've got two samples in total, right, where both are classified as 0 and no one is classified as 1. This gives me 0. Now, that's the best you can do. You can't have an impurity less than 0. It's a positive quantity. And note that here we're minimizing the impurity. So over here, your J0 at this particular question, at this particular node of the tree. So each node of the tree that you see over here that we're going to now, fill them up along the way. This guy over here is asking, is x1 less than A1? If it is true, you've got an arrangement of 2, 0, where your impurity is 0, which means that you don't need to go ahead and ask more questions. So over here, you're sure that this node of the tree right here is a leaf, because there's really no more questions to ask. Your G is 0. You've done a really good job in minimizing your cost. Stop right here. At this question, stop right here. Now, let's go to J1. J1 is when your x1 is greater than A1. What do we have? Well, if this is false, then really all we have is the inverse logic. That is, we've got 0 samples classified as class 0, whereas 2 samples classified as class 1. If you do the math right down here, you go ahead and compute J1, you're going to see that it's equal to J0, that is 0. You do the math, 1 minus k going from 1 till 2, pk square That is 1 minus p0 square minus p1 square. But this time it's 0, not because of the 2 being over here. It's because it's over here. Because how many samples do you have classified as 0? None out of 2 in total. And how many samples do you have classified as 1? All the samples. There are 2 in this subset. Square, which is 0. Going back up to the tree, it's 0, 2, G is 0, and you're done. So when you're... Oh, and by the way, to finalize this, 0, 0, you plug them back in J0, J1, you get a total cost of 0, which is the best thing you can do. Now notice over here, I gave you a really easy example. It's very easy. 4 points, easily separable in 2D. And guess what? Because over here, we ran the classification and regression tree algorithm, the CART algorithm. This is in no way optimal because, you know, we're doing this per feature. Usually, these type of problems are scale up to p dimensions, where p is the number of features. The optimal way of building a tree would not, you know, minimize per feature. It would do this jointly. It would separate all features jointly. Now, in 2D, it doesn't make much sense, but once you go to higher dimensions, you start seeing the difficulty of building decision trees if you were to embed the optimal. Now, with 4 samples, you know, there's not much to see. You don't see how hard the problem is. But if I give you 100 samples and even more, they're not separable, you might get a feel of why the optimal algorithm is highly complex. Actually, the optimal algorithm to build the optimal tree would require you something around 2 to the power, I think it's m, where m is the number of examples that you have in your data set. And I think this 2 would also be replaced by another number if you have more classes. So 2, I think it's for the 2-class scenario, but in any case, it's exponential. That's the most important thing to keep in mind. CART, on the other hand, the algorithm that we just, you know, ran right now to build this tree, is a suboptimal algorithm. It's fast. As you can see, we iterate over features. So it's a recursive algorithm that goes through each feature and builds a decision boundary based on this feature. So it's suboptimal, meaning that the tree that is an outcome of this algorithm is not necessarily the optimal one. But it's good because CART is a greedy algorithm, means that it stands at every feature and minimizes its cost at that particular feature or at that particular node of the tree. Okay? Note that here we terminated the algorithm because we obtained the best minimizer, that is 0 at each leaf. So once you get an impurity of 0, you're sure that you stop there. In other words, you don't have any much more uncertainty on G. And speaking of uncertainty, the Gini impurity is one cost that people optimize. Another one is the entropy. And I'd like to, since I come from a communication background, I like to see it from an entropy background, because entropy means uncertainty. And what's the inverse of entropy? It's information. So the less uncertainty you have, the more information. And entropy really is not only a telecommunication metric, or it's not only a machine learning metric. It's used in a lot of different fields. It actually originated from thermodynamics, when people were measuring uncertainty and disorder or chaos in molecular systems. So so that you get a feel of what entropy is, I actually do have a lecture on entropy, but since we're here, I just want to show you what entropy, why it's that important. Imagine you have a coin flipping experiment, okay? A Bernoulli distribution, call it B, okay? This Bernoulli distribution is parameterized by the probability of success P, that is if my random variable, let's call it, I'm not going to call it x because x is reserved for my data set. Instead, I'm going to call it, let's say z, I don't know, c, okay? C for coin outcome. So the probability that my c is 0 is 1 minus p, whereas the probability where c is 1 is p, okay? And, well, where does the entropy come in play? Well, the entropy over this random variable, so imagine how powerful the entropy is. It measures the amount of information in a given random variable. So my entropy, usually denoted by h, is given by the following formula. So it is minus sum k going from 1 till as many outcomes as you have. So in a discrete case, this is a discrete experiment because you either get a 0 or 1, but indeed the entropy could be extended to continuous random variables. But in this case, this is the definition for a discrete random variable. So k going from 1 till 2, since I have 2 outcomes, pk log pk, okay? So this is p1 first, or p0, and this is p1. So here I might reorder the indices. So it's k going from 0 to 1. So expanding this guy, the entropy, we get a minus p0 log p0 minus p1 log p1. Now you might be seeing minuses here. Whoa. And the first question you might think, oh, is the entropy negative? No, it's a non-negative quantity. It's always, at most, in the best cases, h is 0. And I'll show you what best cases mean. What does a best case mean? So yeah, this is my definition, and and actually, why is this term always is never negative? It's because log p is a probability, and hence it's between 0 and 1. So all my logs are negative. This guy is negative, this guy is negative. So negative times a negative is a positive, negative times a negative is a positive, and p0s and p1s are positive. So you're adding positive numbers. So this guy is always guaranteed to be positive. So replacing p0 by 1 minus p, we get minus 1 minus p log 1 minus p. Minus p1 is p, so we get a p log p. Okay? And if you were to plot h as a function of p, so if we came here and notice that the support of h, if you see it as a function of p, is between 0 and 1, because probabilities take values between 0 and 1. Well, let's evaluate h for p equals 0. P equals 0, well, here we need an extension by continuity. So for p equals 0, we're going to, extension by continuity, because log is not defined at 0, but 0 log 0, we will say that it is 0. Actually, if you evaluate the limit of this guy, when p goes to 0, it is 0. This guy goes to 0, right? So if this guy is 0 at 0, and this guy is also 0 because we get a 1 log 1, which is 0, that means that we've got a 0 over here. Likewise, at 1, this guy is also 0. And it does a shape if you go plot it on any software, or you do some basic calculus, you can find that it takes the following form, where it peaks up at half. So what is this telling us? It's very important, very important. This means that when you're at 0 and you're at 1, you don't have uncertainty. This is true because when the probability of success is 0 or 1, you could, without any trial, know the outcome of your experiment, right? Because when p is 0, then you're sure every time you flip the coin, you're going to get a 0. And when p is 1, when you flip the coin, you're going to get a 1. 0 is heads, 1 is tails, or vice versa. It doesn't matter, okay? And you start getting more uncertainty when the coin is fair. That is, when p is half, when your outcomes are equiprobable. right? So, and this makes absolute sense, because when you have a weighted coin, say it's more towards 0 than 1, say P0 is greater than P1, then you're over here. You start having less and less uncertainty, okay? And likewise, when P0 is less than P1, this guy's symmetric, so you start having less and less uncertainty, okay? So I hope this small argument shows you why entropy is also used instead of Gini impurity. It carries information, because here we're asking questions and we're classifying based on thresholds we're picking at each node, right? So why not also use my J0 to be an entropy? So instead of this guy right here, you could have that your entropy is defined as minus k going from 1 till p. Your pk's will now form your entropy as such, okay? And this cart algorithm would, at each instance of the node, minimize the entropy, that is, minimize the uncertainty of the questions asked. So you pick an arrangement. The arrangement is picked at each node of the tree based on minimum uncertainty principle. Okay? So what we did right now is really introduce you to decision trees, take a very basic example in 2D using 4 samples, and see how a suboptimal algorithm, the cart, would run on this instance. Now, what I'd like to do right now is open my Jupyter notebook and start seeing how decision trees run on classification problems, and how the decision tree could become complex with more and more samples. So let's start by importing the modules that we need. Of course, we're going to need scikit-learn's tree. We're going to import decision tree classifier. We're going to need NumPy for some linear algebra functionality, and we're going to need matplotlib's pyplot to plot. This guy's from, I guess. Yeah. Okay, so now let's create some artificial data centered around some point and with some Gaussian noise. So I'm going to create 4 classes in 2D. The first one is centered around -1, -1, -1, -1. I'm going to add some noise, so some Gaussian noise of standard deviation 0.5. So the way you can do that is as such. Let's say we want 50 samples in 2D. And they're all going to belong to the class labeled as 1 as such. So we'll multiply 1 by a vector of all 1s, or you can leave it as such. Okay? This is our first class. The second class, I'll copy paste this code and just, change the center to -1, 1 and call it x2, y2 and label the target values as 2. Likewise, I'll copy paste those, x3, y3, this time centered around 1 - 1 and give it a label of 3. And last but not least, I have class 4, x4, y4, label it as 4, centered around 1, 1. So those are my 4 classes. Let me run this. And let's stack them all into one data matrix X using NP vertical stack, because I'm going to stack them one on top of the other. X1, X2, X3, and X4. Likewise, Y, I'm going to use horizontal stack because they're row vectors. And I'll stack them one next to the other as such. So this is my X of size 200 by 2, 50, 50, 50, 50, that's 200. And my Y is 200 by 1. Okay? Now, to use the tree classifier, you need to call it as such, decision tree classifier. And this is the way you initialize a tree classifier. Okay. You can pass some parameters over here, like the max depth. Let's set it to, I don't know, 2. That means we're going to accept only a depth of the tree at 2. We're going to stop there, okay? Just for simplicity. And the way you train your model is using fit, y versus x, as such. As such, you have your model ready. Now, to view the tree, we're going to use from scikit-learn, we're going to import tree, as simple as that, and we're going to import graphviz. Now, this might not work properly for you, so I recommend you go to graphviz documentation and you install it using pip install graphviz. But this might not work properly on a Mac, so I recommend you install it using brew. Since I have it, I can import it as such. And what you'd want to do is define your tree data. So you're going to use tree.export_graphviz, pass it your tree classifier, pass it your feature names. For me, they are x1 and x2. And pass it your class names. I'll use an NP array, and be careful, you have to pass them as strings. So class 1, class 2, class 3, and class 4 as such. Okay? Last but not least, you'd want to view your tree. So you go graphviz.source, pass it the data. As simple as that. Now, this is not colored. If you want it colored, you go up here, you pass another attribute that is filled, set it to true. By default, it's false. There you go. Now, what do we have here? As you can see, at each step, so decision tree classifier uses by default the cart algorithm to create this tree. So as you can see over here, the decision boundary is minus 0.052, and I'm going to show you visually on a plot why this is the case. So online, how this algorithm would work, how it would fit the data, how it would predict new coming data, that it would start at the root. It would ask the question, is my first feature less than this value? If so, go left, otherwise go right. If you're at the left node, you ask another question, is my x2 less than this value? If true, you're over here, you classify as 1. If not, you classify as 2. Now, if you're at this node right here, you ask another question, is my x2 less than this value? If so, you're class 3, and if not, you're class 4. Now notice over here, you've got the Gini values, right? You've got those Gini values. And those were the best Gini values to minimize my J cost, the one we talked about over here. Okay, this decision tree classifier would do this recursively. Okay, now let's say you're interested in entropy. Well, by default, this takes a Gini cost, and that's why you see Ginis. If you want entropy, you go ahead and say entropy, run, and here you see your entropy values. There you go. Okay, those were the best entropy values to minimize the total cost. Let's go back to Gini. There you go. Now, if you don't want if you accept more depth, you could remove this. If you remove it, it's unrestricted. Means it could go even more. It could go and it could complicate the tree. Look at how many questions we have. It could be really sophisticated. It could have more boundaries than you could imagine. Okay. But for the moment, let's leave the max depth to 2. There you go. You can also have another attribute specifying the minimum samples, the minimum leaf samples. So by default, it's unrestricted. It's 0. And let's say I put a value of 10. Well, it couldn't fit 10, so it's left with 4. Let's say 1. So this seems to be insensitive with minimum samples. 100, it just gave us some rubbish because it's too high. So I'll just remove this and leave it as 2. Now let's plot our decision boundaries. So I'm going to create a function, call it plot my tree boundaries, pass it my x and y data, and pass it my tree classifier. Okay. The reason I'm doing a function over here is that I'm going to reuse this function multiple times. So I don't want to be rewriting plot functionality over and over again. Let's specify my x1 axis using line space, going from, let's say, -5 till 5. Let's take 200 samples. Likewise, my x2 axis will take the same values, and at each grid point, so I'll define my grid points, x grid 1 and x grid 2 as np mesh grid, pass it my x1 axis and my x2 axis. I'll create my big X grid data as a concatenation of both x1 and x2. Okay? And for each data point on this grid, I'm going to perform a prediction using my tree classifier that has been inputted. I'll pass my X grid and I'll reshape it for plotting. Now, to view the decision areas, it's better to color each area differently. So I'm going to use some hexadecimal code values. So let's go hexadecimal codes for colors on Google. Okay. And I usually use this website to get, my hexadecimal codes. So over here, what I'm going to do is create a color map. So listed color map. And for that, you need to import it from matplotlib colors. So I'll go back up here and go from matplotlib.colors, import listed color map. Run this, all seems good. And so my color map will contain 4 hexadecimal values, each for a color. Okay. Let's pick the colors together. Let's say I want orange, this orange for class 1. Let's say I go back down here. Say yellow for class 2. I like this green. Let's pick it for class 3. Okay. And go back down here. Let's pick something like purple for class 4. And let's store this color map in a variable called my color map as such. And we're going to use a contour. First we plot X grid 1, X grid 2 versus Y predicted, and pass it my color map. Okay. So if I were to run this, function as is right now, let's see what we get. So plot my, actually let me copy paste this. And let's fill those guys together. So my x is x, my y is y, and my tree classifier is the one over here, the one we trained. Tree classifier. If I go as such and go plot dot show, I get an error. And what is x1 at line 5? So I have an error over here. This one is x grid 1 and this one is x grid 2. My mistake. Decision tree classifier object, it's not callable. Why? Oh, okay. So we need to run dot predict. That's a stupid mistake. So run, so we can see the decision boundaries. There you go. We didn't plot the data, but we can see the decision boundaries. Actually, this coincides with the tree we have over here. Why? Well, this guy over here, this line along x1. So let me just label my plot. So plot x label is x, and plot y label is x2. So my x1, go back here. Here's the first question. Is it less than minus 0.052? Here's your minus 0.052. And your second question is based upon x2. So you have two close but different decision boundaries. The first one is minus 0.059. Second one is minus 0.07. So the line separating the green and the purple regions is a bit higher than the one separating the yellow and the orange region. So here's your minus 0.059 and here's your minus 0.07. Now let's go ahead and plot the data, see how good this classifier is. So we need to plot my 4 data sets. Let's go ahead and plot x1, first column versus its second column as such. Give it a label of class 1. And right here, plot.legend. So as you can see, there's scribbles. That's because I didn't specify the format of plotting. So I'll go ahead and plot it in maybe red circles as such. Okay, as you can see, this guy is not classified properly, but you can overfit your data. This is the best decision boundary in a Gini perspective. We're going to do the same thing for my other 3 classes. So each class I'll give it a different color. So let's say blue, black, and magenta. This guy's x2, x3, and x4. Likewise here. And there you go. Here's your 4 classes. So this is how your decision tree classifier works based on the questions computed according to the CART algorithm. Now, an even cooler feature of decision tree classifiers is that it is capable of giving you soft decisions. What I mean by soft is that the probability of new arriving samples, what is the probability of that sample being in a certain class? So what I mean by probability is that you go ahead, tree underscore classifier. Let's say I pass it a point over here in the green region, that is class 3. So let's say, I don't know, 3 and minus 4. So 3 minus 4, and I always forget the dot predict. So here it's classified as class 3. This is a hard decision, but let's say you're interested in probabilities, a soft decision. All you need to do is predict underscore proba for probability. And there you go. It gave you an exact 1, so it's 100% sure. This tree is 100% sure that this point belongs to class 3. Well, let's get it closer to the boundary, see what happens. So instead of a 3, let's say we go to 1. And instead of my minus 4, let's pull it up to minus 2. It's still sure. So let's get it even closer. So 0.1 and minus 0.2. It's still sure. Well, let's pull it up to the positive sense. Let's put it over here, maybe. 1. And there you go. With 0.96% confidence, it's classified as class 4. So up here, because I pulled this guy up. Let's pull it back down. Still here. Put it here. Still here. Put it here. Still the same. Still the same. Still the same. Let's go minus 0.01. Minus 0.05. Minus 0.09. And whoop. It's 100% sure it's in class 3. So this is how you get a sense of probabilities when working, if you're interested in a soft decision on tree classifiers. Now, a natural question here is, how good is our decision tree classifier? This is a very important question to ask. And another important question is, in which sense? So let's say I'm faced with a bit of perturbation. So in some applications, your data would be rotated. What I mean by rotated is simply you just rotate those data. Keep in mind that tree classifiers work super good with orthogonal decision lines as such. It works almost perfect. Now let's say I rotate my data a bit, and what I mean by rotate is that simply I create a givens matrix. So a givens matrix rotates any data point by an angle of theta about the x-axis. Okay, this is in 2D, but indeed the givens matrix works in n dimensions as well. So in n dimensions, we mean that we rotate per axis. So in 3D, this would be a 3-dimensional matrix composed of possibly a product of 3 givens rotation, each about a certain axis. Okay. And to rotate a point in 2 dimensions, all you have to do is multiply your data point by this givens matrix. You get another data point, but shifted by angle theta. Let's do this quickly and see how this classifier would be trained in that case. So let's define a theta that is in radians. So you need to do the conversion. Let's say it's 30 degrees. So you multiply by pi, you divide by 180. This is your theta. Let's create a G matrix. That is my givens matrix. So it's an NP array. It's a 2D matrix. So you've got a cosine theta. Then you've got a minus sine theta. Then you've got a sine theta. Then a cosine theta. Okay? You rotate your data, so x rotated is nothing other than x dot g. Okay? So what we're doing over here is x times g. So this is your x rotated. Why? Because each data point is multiplied by your g as such. Okay? Now you might be asking, oh, but this g over here is, you know, multiplied by x1, x2 on the left side, so it's pre-multiplied, whereas here it's post-multiplied. Where don't forget that your x over here is a row vector. So applying the transpose, you get a form like this. But with your minus sine theta over here and your sine theta over here, so instead of rotating about the x-axis, you'd rotate over the y-axis. Okay, but that doesn't matter. I just want to show you the effect of rotation when building decision trees. So this is your data. Your y doesn't change. Your classes are still the same, right? And so let's create my tree classifier. Let's call it rotated tree classifier. See how it behaves with rotated data. So decision tree classifier as such. And now let's run this rotated tree classifier. Let's fit it on the x rotated data versus y as such. It's done. Let's open a figure. What was the name of the function? Let's copy paste this guy over here. So my x is now x rotated, and I'm using the rotated tree classifier. And last but not least, I'd like to show my plot. As you can see over here, you get more than one boundary. You get 1, 2, 3, 4, 5, 6, 7, 8, 9. You have a lot of boundaries. And as you can see, it's not that clean, right? It's not so clean. If we want to go ahead and take a look on the decision tree, copy paste this snippet of code, nothing changes other than the name of the classifier. So it's rotated tree classifier. And as you can see, it's huge, it's big, it's really complex. So look how many questions. You start here, first question on x2, then you've got other questions on x1. So it keeps asking you questions. You've got a lot of leaves and a depth of 1, 2, 3, 4, 5, 6. So it's really complex. So moral of the story, decision trees doesn't work good with, it doesn't like rotated data. It likes data where decision boundaries could be fitted orthogonally to each other. And that's it. This solution is solved using PCAs. So with principal component analysis, you could apply a principal component analysis on your data and extract important features from the data, and then feed those features to the decision tree. But we're not going to do this over in this lecture. I just wanted to show you how sensitive decision trees are towards rotated data. Now, as we mentioned earlier, decision trees are also capable of performing regression tasks. It functions almost, so the principle is still the same. That is, we're going to build a tree using the same methodology. Let it be an optimal algorithm, let it be CART. But instead of basing our decisions on Gini or Entropy, we're going to base it on our old friend, the MSE, the mean squared error. What I mean by that is that at each node of the tree, we will have a cost function, as we did before, the j, k, a of k, but this time your j0 and your j1 would both represent MSEs, okay? So your j0 would be MSE0, that is for those points at, so again, class 0, where the points such that their xk's were smaller than ak, and class 1 was the opposite. Okay, so j0 would be the MSE for those points in class 0, and j1 would be MSE for those points in class 1. So how do you compute the MSE in this case? So for those points that you pick in class 0, let's say we're computing j0. So here we've got the j0, here we've got the j1. j0 would then be computed as the mean squared error. So it's the sum of yi's minus your predicted y hat square over i's that fall in class 0. And likewise, j1 for I that fall in class 1, same way, yi minus y hat square. Now, a question here is that, okay, I have my yi's, and after this CART algorithm runs, I could, find my ak so that I separate both classes 0 and 1. But how do I compute my y hat? Well, that's a good question. Actually, y hat is taken as the average over those points. So over here, your y hat would be 1 over m1. So you've got m1 points. You take the average over all yi's that fall in class 1. And same over here. Your y hat would be 1 over m0, sum over I in class 0 of your points over there. Okay? So really, that's the only difference. Instead of having the discrete values 0 or 1 to compute Gini and impurity, here we're computing MSEs, and at each node we seek to find the minimum MSE, the split between the samples that minimizes the MSE at each node. Okay, so let's go to Jupyter Notebook and see how regression decision trees work with given data. So let's create some artificial data. Let's say I've got, I don't know, 400 points, and I'll pick my X data to be uniformly random. So this guy returns, let's see what this guy returns. Is it between -1 and 1, or is it between 0 and 1? Let's plot those. It's between 0 and 1. So let's say I want my points to between 0 and 5. Here's my points. Plot it to make sure. There you go, between 0 and 5. Okay. And let's form a function. Let's take a cubic function. So let's say I'll take x minus, I don't know, 1 cube, and multiply this by, I don't know, 3, and say that's my y. Okay, this is my x and this is my y, and let's add some noise to y. So we'll add some Gaussian noise as such, and there you go. Let's plot our data. Always include dots in such plots. So there you go. Let's add some more noise. 0.25. Still not high, because here, look, it's really high. So let's add some more noise, and there you go. Okay. Okay, let's say we have those data and we'd like to perform regression. We'd like to perform regression using decision trees. So you'd want to import from scikit-learn.tree. You'd want to import decision tree regressor. Okay, and you create your tree regressor using decision tree regressor, and here is where your max depth plays a fundamental role in how your predicted values will behave. Let's say I start with a max depth of 2 as such. Okay, I have this guy, max depth of 2, and I'm going to fit my y versus x. Okay, so let's create a line space to plot. Line space 0 till 5, take 500 points, reshape for plotting. Let's do a prediction. So y predicted tree regressor dot predict, put x1, open a plot, y versus x. Let's plot the data points as we did in blue, and then on top of those we're going to plot my grid points versus their predicted values in, I don't know, maybe black, dotted black as such, joined by lines. Okay, and last but not least, I'll show my plot, and there you go. So as you can see, you have levels. So the decision boundaries are the vertical cuts as such, and to see those values on a tree, let's go back up here, copy paste this snippet of code right down here, and pass it my tree regressor as such. This time I only have one feature, that is my x value, and I don't have classes. So I'll remove this, I'll run this. This is not matching. Let me remove this, run, and there you go. So decisions are solely taken based on x because that's all we have. That's the only feature we have. And MSEs instead of Ginis. Now, this 3.891 is basically over here. This guy right here. It starts by separating the points left, and right. Then your 3.054 is over here, and your 4.522 is right here. And so you've got 3 decision boundaries, where you end up with 4 different y hat values. And this 4 comes from the fact that it's 2 squared. If this is increased to 3, you've got 1, 2, 3, 4, 5, 6, 7, 8. 2 to the power 3, that's 8. And here's your values. Okay? Note that here's your values. Note that those MSE values are the minimum you can achieve using this CART algorithm. Note that if you run the optimal algorithm, you might get a better, tree, in the sense that your MSEs, your global MSEs would be lower than the current ones, but this is the job of the cart algorithm. Okay, let's go up to 4, see what we get. In principle, you get 16 classes, but 16 regressed values. Let's plot them in red. So let's count this together. Actually, let's zoom in first. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There you go. This is how this guy works. And the way I see regressor trees, decision trees, is that it's a sampler. It discretizes your noisy data into discrete ones using a decision tree. That's all it does, right? Because, like it or not, you're picking your samples and you're averaging those samples in this class to form a constant level, okay? So this is a piecewise constant function. You can view your predicted values as a piecewise constant function. That's what it's doing, okay? So that's all I have to say about decision trees for regression tasks. And now let's create a case study where we're going to use decision trees for stock classification. So we're going to read data from stock markets and we're going to predict buy and sell signals. Is this a good way of doing that? Well, it depends on different metrics. We're going to see that after performing buy and sell prediction signals, we're going to, analyze, we're going to build a classification report. We're not going to do regression. That's one. I've tried decision trees for regression on stock data and it doesn't do a good job. The way this is explained maybe is because you're classifying your, signals. So if your goal is to, perform trading, fast trading, this might not be a good option because look, all those fluctuations are, not captured in this class, right? All those fluctuations are, constant. On a short term, this is not going to be a good solution. On the long term, maybe, you see those jumps, but it doesn't, it's insensitive to, short-term fluctuations. So we're going to see a reasonable way of building decision trees for stock market analysis. Okay. So for that, let's start by importing some modules. So I'll start by pandas data reader.data as web, and from pandas, I'm going to import the date time. I'll import numpy as np. I'll import scikit-learn.tree. Actually, from this, I keep doing this mistake. From this, import from scikit-learn.tree, import decision tree classifier as such. Okay. Do we need something else? Well, I'll be using pandas to manipulate data frames, and I'll be using matplotlib.pyplot as PLT. Let's specify a start date, so datetime.datetime from 2010 till date of today. So datetime.now. Okay. Now let's create a data frame where we will be reading stock Google. So I think the ticker name is Google without the E, from the Yahoo API start end. There you go. And to see our data, I'll be calling plot.plot df. Actually, your data frame will look something like this. You've got the high price, low price, opening, close, and the volume, and the adjacent closing price. So df, I'll be plotting the closing price of Google. There you go, up to the moon. Okay. So the question here is, what am I going to be building my decision tree on? Is it based on opening price? Is it based on closing price? Well, as I mentioned, I tried regression decision trees and it didn't give me a good job. So here we're going to perform classification. Is it a good, price to buy, or is it not? So binary classification, that's what we're going to do. And binary classification is going to be based upon returns. So for returns, I'm going to create a new column that is going to take the closing price, and I'm going to perform a moving average over 60 days, and I'll shift back 60. We're going to use, what that means is that I'm going to average 60 days in the future, compute the returns, the relative returns, see if it's positive or negative. So this PCT stands for percentage and change. So we're computing a percentage change, a relative change on 60 days. Okay. Let's create a list of my features. I'll base my decision based on, so I'm going to feed it more than one feature. I'll feed it everything I have. So high, low, close, volume, and adjacent close. Okay, this is my X. It's going to be based on this list of features. So if you want to view some values of X, there you go. High, low, close, volume, and adjacent close. But my Y is going to be either 0 or 1. So I'll go ahead and look for values where the return is positive. If so, classify it as 1, else as 0. There you go. So this is my X, and actually let's take a look at DF. So this is my DF. Here we've got negative, 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 doesn't matter. And here's my Y. So the first 5 values of my Y are 0 due to the negative. If I go ahead and look into more values, we've got a positive over here, which means there's a positive return. Okay, this is data averaged over more than 10 years. So imagine, there's a lot going on in this stock. So this is my data. Here's my X, here's my Y. And now I'm going to create, before creating my decision tree, I'm going to split my data. So to see how good my decision tree is performing. So from scikit-learn if you remember in the previous lectures, we've used model selection. From model selection, we imported train, test, split as such. So I have my X train, my X test, my Y train, and my Y test. Using train, test, split, we'll pass it my data. I'll use a test size, let's say 0.3 as such. And if you want, you can pass a random state, whatever, as such. So I've split my data. Let's see the sizes of the data. So let me print xtrain.shape. Actually, let me print all their shapes. The X test, the Y train, and the Y test. There you go. 2002 for the training data and 859 for the test data. Let's create my tree classifier object using scikit-learn's decision tree classifier. Let's limit the max depth to 3, and let's limit the min samples, I don't know, to 6. Now let's call tree classifier to fit my data. So fit xtrain, ytrain, and there you go. Now let's perform the prediction as such. So tree classifier dot predict on the testing data this time. There you go. Now that's it. We have our data. We have it all. And now let's check some performances. So from sklearn.metrics, import classification report as such. So my report is a classification report, passing in the Y test and the Y predicted as such. And finally print my report. And there you go. But you can do better by going back up here, and there you go. You've got the sell signals, which are really accurate, 0.95, but the buy signals are 66%. The recall is really good, 1. Got an F1 score for 1 for a buy signal, 79, and 13 for the 0. This is actually not bad for this kind of stock, for Google. Got a 95% precision for sell signals, which is awesome. Let's play around with those values, because let's say you don't want to average. You want only, you know, just look into the future and that's it. No averaging. Running all this drops a lot. So from 95 to 47%. That's bad. Okay. Let's raise this up to, I don't know, 30. You start seeing some improvement. 60. Back to what it was, 95 and 66. Let me change my random state. You actually do get good values, so it's always more than 50%. 71, 69, again 71, 69, 80%, 65. So what we're doing here is reshuffling the data and recreating another decision tree classifier. Okay. Now, if you're curious, as I am, to see how the tree looks like, we're going to do as before. So from scikit-learn, import tree, import graphviz, create my data, tree.export, graphviz, pass it the tree classifier. We want it colored because we like colors. Pass it the feature names that I believe is over here, list of features, and pass it the class names, which is an NP array of buy or sell. Then go ahead and call graphviz.source on the data. And there you go. This is your tree for this type of data. So it first look, it has 1, 2, 3, 4, 5, 6. Actually, no. We've got 5 features: high, low, open, close. We've got high, low. We don't have the open. Sorry about that. Actually, let's see what happens if we put the open. So open, there you go. I didn't try that, so let's go ahead. Lower values. So again, not as good. Okay. So this is the tree that was constructed. It first looked at the high price. Is the high price less than 1993? If not, is the closing price less than this guy? If not, then you have a sell signal. Now, if the high price is less than this guy, the closing price is greater, which is what you want, than this guy, you go back down here, you ask this additional question: is the additional closing price greater than this guy? So it has to be, the closing price should be greater than this guy, the adjacent closing price should be greater than this guy, and the high price should be greater than this guy, so that you go down here and you have a buy signal. Okay, so you can really get as complicated as you want with this tree by increasing the number of max depth and the minimum samples of the minimum leaf samples. You can go ahead and experiment with other stocks. Let's say zomedica. You go down here, there you go. Really good job. And actually zomedica is really, you know, it experienced a drop, then a pump over here. It's not like Google, which is always going up. No, it had, you know, it was doing good. And 2019 it dropped, remained almost constant. Actually, it dropped, you know, it dropped a lot. No, if you zoom in over here, there's like a factor of 5, 0.5, 0.1, then times 20. And so we were that much, we're 82% good for sell signals and 69 for buy. What else do we have? Let's go ahead and see Elon Musk, Tesla. So here's Tesla. Go Tesla. Run. And there you go. 88% good for sell signals and 60% for buy signal. Actually, it's the opposite. 60% for sell and 88% for buy. Okay, so that's about it. That's all I have to say on decision trees. I hope you enjoyed this lecture as I did. If you did, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I hope I'll see you in future lectures.